Hello there, this is an Algebra 2 lesson. It is Chapter 5, Section 3, and today we are talking about polynomial functions. And the first thing we want to go over is what the general form of a polynomial function is. I don't want you to get too scared. This is basically the general form of a polynomial function. Oftentimes we call it p of x. And I just want you to be aware that although you see a lot of scary letters here, all it really is saying is that the degree of the exponent is decreasing in order from largest to smallest. In other words, this says x to the n power, this is x to the n minus 1 power, then it would be n minus 2, n minus 3, n minus 4, and eventually you'd get down to x squared, x to the 1, and x to the none, or basically it's not there. So for example, if you had x to the 7th power, the polynomial would only be in standard form if you were going x to the 7th and then the next biggest, which would be n minus 1, so n in this case would be 7, and 7 minus 1 would be the x to the 6th, n minus 1 would be 6, and then n minus 2 would be 7 minus 2, so x to the 5th, and then x to the 4th, x to the 3rd, and eventually you get to x squared, x, and then no x, the constant term. And so the coefficients, the a sub n, is just there to let you be aware that it's attached to the nth degree term, and the n minus 1 goes with the n minus 1 degree, and the a sub 2 goes with the 2nd degree, and the a sub 1 goes with the 1st degree, and on and on story goes. So it actually looks a lot more complicated than it actually is. Basically, you want to put the terms in order from biggest exponent to smallest exponent in order for it to be in standard form for a polynomial function. So here we have some examples of how we name polynomial functions. So I have the name here, the expression of what it would look like, what the degree would be of that polynomial, and then the leading coefficient. Now remember, we talked about this already in 5.1, that each term has its own degree. So the degree of this term would be 2, the degree of this term would be 1, and the degree of this term would be 0 because it doesn't have an x term at all. However, when you talk about the degree of the polynomial, you want to go with the leading term and the exponent of that term. So, constant, that's when we have no variable at all. So that would look like just a number, like 12, and the degree would be 0, and in this case, the leading coefficient would be 12. And then we have the linear case. In the linear case, you would have x to the 1 power. So you don't usually write the 1, but I put that there so you can see. It's x to the 1 power, so the degree would be 1. And in this case, the leading coefficient would be 4 because it's the coefficient of x to the 1 power. And then we have quadratic. In the quadratic case, we have x squared. And that's the biggest term, that's the biggest exponent for these three terms. So the degree is 2, and then the leading coefficient is 5. Then we have our cubic. And in our cubic case, the degree is 3. And the leading coefficient is 8. In general, we go back to the original, and in general, we have x to the n power, the degree would be n, and the leading coefficient would be a sub n, whatever is in front of that biggest. So that's just the general form. All right, so here we have an example, and it says, state the degree and leading coefficient of each polynomial in one variable. If it is not a polynomial in one variable, then explain why. So we'll start with A, and the first thing you want to do when you're doing this is to make sure that all of the terms are in order from biggest to smallest. So we have 5, and then 3, and then 2, 1, none. So these are in order. The x to the 4th term is missing, but that's okay as long as they're in order from biggest to smallest. So that would mean that this is my leading term, and so they're asking for the degree. So this is a polynomial in one variable. The only variable here is x. So then that means that we have to go ahead and give the degree. So our degree would be 5, and our leading coefficient would be 8. And it's that simple. In part B, this would be not a polynomial in one variable, and the reason why it's not is because you have a product of x and y in this case. So we can't have two different variables like that there. So for letter B is not a polynomial in variable, so therefore we can't talk about the degree or the leading coefficient. In this case, these are all x's. However, they're not in the right order. So the first thing you want to do is put them in the right order. We have -4, x to the 8th. This exponent is larger than this one, so it's not in the right order. And then we would have positive 3x to the 4th, positive 6x cubed, and positive 2x. So now all of our terms are in the right order, and now we can say that the degree is 8, because that's the biggest exponent, and our leading coefficient is -4. So it's not very complicated. Now I want you to do it yourself, number 1, and then we will move on to example 2. In example 2, we are going to be evaluating a function, and sometimes this can get tricky, but here's our function, f of x equals x squared plus 2x minus 3. You might remember that finding something like f of 1 is very simple. If I had asked you to find f of 1, all you would do is plug in 1 into the x values and then simplify your result. But that's not what we're doing here. Here we're going to be substituting something a little bit more complex than just an integer or a number. It says find f of 3c minus 4 minus 5 times f of c. And I want you to be very clear that when it says minus 5 times f of c, it means minus 5 times the value of the function when c is replaced, when c replaces the x. When you read this, f of 3c minus 4 means the value of the function when the x variable is replaced by 3c minus 4. So the easiest way to do this is to take each piece separately and then combine them at the end. That's what we're going to do. So the first thing I want to do is find f of 3c minus 4. So this is now my input, 3c minus 4. So I go to my f function, and it says to do x squared plus 2x minus 3. I use parentheses instead of the variable to remind me that I'm going to be replacing the x variable with something else. And that something else is 3c minus 4 in both x values, or x spots. Now, you need to remember that when you do this binomial squared, it is not 3c squared minus 4 squared. You actually have to FOIL that out, or you have to use the formula that we've already done before. The formula, if you don't remember, if you have a plus or minus b quantity squared, is always a squared plus or minus 2ab plus b squared. Lots of students forget that all the time. I'm just reminding you, and I'm going to be using the formula. So that's going to be 3c squared is 9c squared. This is a minus, it's going to be minus 2 times a times b. So it's going to be minus 2 times 3c, and minus 2 times 3c is negative 6c, and then negative 6c times negative 4, or times 4. So negative 6c times 4 is 24. And then plus b squared, so plus 4 squared, so plus 16. All right, so far we get 9c squared minus 24c plus 16. And then we're going to distribute here, so we're going to get 2 times 3 is 6c, 2 times negative 4 is negative 8, and of course minus 3. And now we want to simplify all that, so we're going to get 9c squared. We have negative 24c plus 6c, so that's going to give us negative 18c. And then we have 16 minus 8, which is 8, and 8 minus 3, which is 5. So right now what we know is that f of 3c minus 4 is equivalent to 9c squared minus 18c plus 5. That's just this part. Okay, now what we want to do is we want to find f of c. 5 times f of c. Okay? And the reason why we want to do that is so that afterwards we can actually subtract the two results. And this is a minus here. So I already found this. I'm going to find 5 times f of c, and then I'm going to subtract my results. So the first thing you want to do is leave the 5 there. F of c is going to go in here, and f of c basically means to take the f function and replace all the x's with a c. So that's going to be pretty easy to do. You're going to get c squared plus 2c minus 3. I'm just replacing the two x variables there with c's instead. And then the 5 is out here, so it's 5 times all of that. So now I can distribute my 5 and get 5c squared plus 10c minus 15. So now I have the two pieces that I need, and all I have to do now is subtract the two. So I've got 9c squared minus 18c plus 5 minus my result from 5 times f of c, which is 5c squared plus 10c minus 15. Be very careful not to forget to distribute your negative. This would be minus, and actually what I'm going to show you how to, an easy way to keep track of your stuff. I'm actually going to write the like terms in a vertical column to make it easier to subtract. So I'm going to say negative times 5c squared is negative 5c squared. So I'm going to go ahead and put that right underneath the 9c squared because they're like terms. Then negative times positive is negative 10c, and I'm going to put the negative 10c right underneath the 18c because again they're like terms. And negative times negative is positive 15, and the positive 15 is going to be placed right underneath the 5 because they're like terms. So now when I add these together, I'm going to get 9c squared minus 5c squared is 4c squared. Negative 18 minus 10 is negative 28c. And 5 and 15 is 20. And here is my final result. 4c squared minus 28c plus 20. Alrighty, so now I'm going to let you do these two on your own, and then we're going to move on to some of the behavior of polynomial functions. Alright, and first up we have basically a summary of the graphs, general graphs of polynomial functions. And so there are 6 up here. We have the constant function, and the constant function is the one that doesn't have the x variable in it at all, and its degree is 0. We already saw that earlier, and the graph of it would look like this, basically a horizontal line. Then we have the linear function. You've seen that before as well. Its degree is 1, and it would look something like that. Obviously, they could have a different slope. It could have a negative slope, but that's in general what it looks like, a line. We have our quadratic function, which of course we've seen a lot in the last chapter. Degree 2, and this is what it looks like. This is a negative x squared, but it has a general shape of a parabola. You have your cubic function, degree 3. And so your cubic function kind of does this little guy. And then we have the two new ones, which are the ones that are highlighted here. Quartic functions would be degree 4, so x to the 4th power. And that would look like this, kind of like a W. And then you have a quintic function, which is degree 5, and it would look something like this. All right? So we also want to talk about the end behavior of polynomial functions. So this is kind of just, each of these functions is just a generic example of even and odd. Okay, so basically what I have on the left is even degrees, and on the right I have odd degrees. So even degrees would be things like x squared, x to the 4th, x to the 8th, x to the 12th. Odd functions would be, x to the 1, x to the 7, x to the 13, those kinds of things. But for the ease of our graphs, I've chosen x squared to represent the evens, and I've chosen x to the 3rd power to represent the odds. But the information would carry over to any even function or any odd function. First and foremost, we have over here even number or no real zeros. If you have an even degree, then you are going to have an even number of real zeros, and the zeros, by the way, are the x-intercepts. So it doesn't have to have x-intercepts, but if it does, they're going to be an even number of them like this. So then we have 2 x-intercepts, like in these 2 examples. Obviously, you've seen some parabolas that never cross the x-axis, so it's either going to have an even number of real zeros, or it's not going to have any real zeros at all. And we've seen that where the parabola is kind of up here and it never crosses the x-axis. In the case of odd functions, these 2 cases here, you're either going to have, or you're always going to have, an odd number of real zeros. Like in this case, you have 1 x-intercept, so you have 1 real zero. In this case, you can see that it's crossing here, it's crossing here, and it's crossing here. So that's 3 zeros. And again, that would make sense because it's an odd degree polynomial. So they're always going to have an odd number of real zeros if they're an odd degree polynomial. And they're always going to have an even number of real zeros or no zeros at all if it's an even degree polynomial. All right, enough about that. So, end behavior. The end behavior is talking about what the function is going to do when x approaches infinity, when x gets extremely large or extremely small. So when we say approaches infinity, we're talking about as x gets extremely large or x gets extremely small in the negative direction. Okay? So if you have an even degree and the leading coefficient is positive, what's going to happen is that eventually both ends of the polynomial are going to be going up. Okay, if you have an even degree but it's a negative coefficient like the negative x squared, you're going to have both ends of the polynomial going down. So basically how that gets explained or written out, and that's the part students don't like very much, but I'm sorry, you have to learn how to do it, is this right here. This is saying f of x, so the y values. The y values here are getting bigger and bigger and bigger and bigger, okay? So the y values are approaching positive infinity because they're getting bigger and bigger, as the x values are approaching negative infinity. So these y values are getting bigger and bigger and bigger the farther you move out in the negative direction. That's what that means. So f of x, this little arrow means approaches. So f of x approaches positive infinity as x approaches negative infinity. The second statement is much like it, only this time we're going in the positive x direction. So the y values here are also approaching infinity as x approaches positive infinity. The domain for this function is all reals. All polynomials have domains that are all reals, so all of them will have that. But the range is basically the y values, and the y, this is saying the range is going to be the y values bigger than or equal to the minimum. So here's our minimum, so we're not going to expect to find any y values below that point. So my range would be from this point onward, so greater than or equal to the minimum of the graph. Okay, so in the case of the negative coefficient, still even, you have that the y values now are going down, so the y values are approaching negative infinity as x approaches negative infinity. And then the y values on this side are also going down, so the y values are approaching positive, oops, that's actually wrong, I wrote it wrong in my notes, let me correct that for you. So here we want to say the y values are approaching negative infinity as, so these y values are going down, 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 negative infinity as x approaches positive infinity. All right, and again, domain is all reals. And in this case, the range is going to be, here is your maximum. In the case of, this is a minimum, and here we have a maximum. So your range is going to be all the y values that are less than that maximum. So that's what it says there. Then you have over here, your odd functions. So in the case of the odd functions, you always have one arm going up and one arm going down. In the case of the evens, the two arms are always, and when I say arms, I mean the end of the function, they're always together. They're always both up or both down. In this case, you always have one of each. They're either one up, one down, one up, one down. So here we go. In this case, we're saying that as f of x, so we're going to f of x, or the y values, are going down, down, down. They're going to negative infinity as x is going to negative infinity. And then on the other side, the y values are getting bigger and bigger and bigger as x gets bigger and bigger and bigger. And in this case, the domain and the range are both all reals. And then in this last one, you have the opposite of what you had in this one. And so here we have f of x, the y values are getting bigger, so they're approaching positive infinity as x approaches negative infinity. And then on the other side, the y values are approaching negative infinity as x approaches positive infinity. But again, domain and range are all reals. That is important as we do this last example, because they want us to describe the end behavior for each graph, determine whether it represents an odd degree or an even degree, and then to state the number of real zeros. Okay? So we're going to do that perhaps in a different color. Okay, first and foremost, describe the end behavior. So the end behavior we're going to do that first is going to say f of x, so the y values are approaching on the left, which is always where you start, they're approaching negative infinity. They're going down, down, down. So the y values are approaching negative infinity as x approaches negative infinity. Then you have on the other side, the y values are approaching negative infinity again on this side as x approaches positive infinity. So as x approaches positive or negative infinity, the y values are approaching negative infinity. Okay, and that tells you that both of the arms are down together. So that means that this is going to be an even function. So we described the end behavior. We now know that it's an even degree because they're both going down together. And then it says take the number of real zeros. We know that it should have an even number of real zeros, or it should have none. But in this case, it has an even number. There's one here and one here, so you have 2 real zeros for part A, at least. And then we'll do the exact same thing for part B. And in part B, we have one arm up and one arm down. So that tells us it's going to be an odd degree. And the number of real zeros, we have 1, 2, 3, 4, 5 real zeros. And our last thing is to actually state the end behavior. So we're going to positive infinity as x approaches negative infinity. On the other side, we are approaching negative infinity. So this arm is going down, down, down. We're approaching negative infinity as x approaches positive infinity. So that's pretty much all you have to do is describe the end behavior, determine whether it's an odd degree or an even degree, and then state the number of real zeros. So if you can do that for these 2 examples, then you will have completed your notes for this lesson, and I will see you in class, and thank you for watching.